So again, we described the structure of the liquid crystalline materials. I would just like to briefly tell you about a couple of applications of these materials. So as we mentioned, the surfactants are just one example. Many of them simply happen to be surfactants because of their polar nature. And this is just a phase diagram of a particular material that, for example, you can see that the material structure itself can be relatively complex. Depending on the concentration of the solvent, depending on the temperature, you can have different phases or different varieties. So for a given material, the material itself can have different types of a structure. And these are just a couple of examples. For one specific molecule, you can have this layered or you can have these spherical type of structures. And these phase diagrams can be relatively complex. For example, the reason why the soap works as a soap is, so the surfactants in general are used to merge immiscible liquids. So the reason why you need to use a soap to wash your hand is because the oil and water are not miscible, right? So you need something that will attach at one end to the oil and the other to the water. And this is, for example, this happens to be a liquid crystalline phase by the definition. As I mentioned, these phases can be much more complex, and there is an entire field of material science that deals with them, So another example that I would like to mention is that typically when we think about liquid crystalline materials, we think about them as being liquid-like, but a material that is produced from a liquid crystalline nematic phase is called, one example is Kevlar. So it's a polymer that has a liquid crystalline phase, and you start from a nematic phase in a liquid, and then you cool it down and you process it in a way that these molecules are highly aligned, so the orientational order is preserved, and yet you have a solid and flexible material. So the Kevlar itself is, again, extensively used. It's resistant to heat, it's resistant to impact, etc. And the final example of a liquid crystalline material application would be probably the most famous one, is the liquid crystalline display. And you're probably not old enough to remember these types of watches, but in each pixel of this liquid crystalline display or watch, there is one cell that looks like this. So each, for example, part that is, for example, representing this number 1, there would be one cell that looks exactly like this, and this representing the number itself. But the main message or the main feature of this is that the liquid crystalline material is sandwiched between two transparent electrodes. Oops. So this would be transparent electrode, and this would be another transparent electrode. And I can apply an electric field in one direction or the other, for example, in this direction. So in the initial state, the molecules of the nematic, or the material itself, or liquid crystalline material, are arranged specifically in the way that they start in this twisted structure. So the molecules in this layer are in this direction, and then you twist them, and you end up with a configuration that is perpendicular to this. And the reason for that is that you start with a polarized light. So you have a source of light. Either it's, for example, the source of light that is in this watch, or sometimes it works on the reflection. You simply take the sunlight. But the light is coming from this side, and then it's polarized. There is a polarizer that makes this light polarized in a certain direction. And if this liquid crystalline material is twisted in a way that is described here, then the polarization of the light will change accordingly. So if you have a light that is polarized in this direction, because of the nature of the molecules, they will shift the polarization of the light. And this polarizer is perpendicular to this one. So in this particular state, the light will go through, right? So this polarizer is perpendicular to this one, but because the liquid crystalline material changed the polarization of the light, at the end you will see the light coming out. However, so this would be the case where you do have light. If you change the orientation of these molecules, so for example, if you apply an electric field, and if these molecules have a dipole moment, there will be a torque that is acting on the molecule itself. So the molecules will align along the length of the electric field, and then you lose this polarization change, right? So the molecules are not anymore in the horizontal position, now they're vertical, and basically the light goes in the polarized state as initially defined. And because this polarizer is perpendicular to the first one, no light will go through. Is it clear? So the basic idea is that you start from a polarized light, and if there is the liquid crystalline phase that is in the horizontal position, the light will be changing polarization and it will go through. But if that doesn't happen, the light will be stopped by this polarizer here, and no light will go through. So it's simply by applying a field in between these two electrodes that have to be transparent, you will get on and off. So I can ask you a question. What would happen if I froze this watch? I tried it. So if I take this and I put it in a freezer, what would happen? Would it still work? Why wouldn't, so most of you say no, okay, that's a no. Why doesn't it doesn't work anymore? Is it because of the battery? Let's assume that the battery works. Why it won't work? So what happens with the material? Yes?
The liquid crystal needs to be able to rotate the light. That's only possible when it's a liquid crystal.
That's right. So the molecules themselves have to have the ability to change the polarization of the light, and that's possible only if they're in the liquid crystalline phase. If you freeze them, the material becomes crystalline, right? And you lose this possibility. And just to show you an example of, so this would be an example of two droplets of the liquid crystalline material before and after you apply an electric field. So if there is no electric field applied, the light will go through. And if you do apply a field, the molecule simply switch the direction and there is no light that goes through. Okay? So with this, we will stop. With this, we are completing the discussion about the applications and the structure of the liquid crystalline materials. What we will do next time is that we will start a discussion about defects in materials. It's a completely new topic and a very